Here's a thought that feels almost illegal to say out loud. Time may not be the fundamental backbone of reality, not in the way we instinctively believe it is. Recent scientific discussions point to a deeply unsettling possibility. Time might not be a built-in feature of the universe, like a track everything rides on. Instead, it may be something that only shows up when deeper quantum rules line up in just the right way, an emergent phenomenon rising out of the bizarre machinery of quantum mechanics. And if that sounds impossible, that's exactly the point. Because if time isn't fundamental, then our most comfortable intuitions, past versus future, cause versus effect, even what it means for the universe to change, might be closer to mental scaffolding than objective structure. In this documentary-style breakdown, we're going to trace the chain step by step. How physics traditionally treated time, how Einstein reshaped the entire concept, why quantum mechanics complicates everything, and why some researchers now argue that time may emerge from quantum entanglement, and only from that. For most of scientific history, time looked like the simplest ingredient in the cosmos, a steady, uniform flow, never speeding up, never slowing down, and never caring who was measuring it. In classical physics, time acts like a perfectly stable backdrop. Events unfold in time the way objects sit in space. That's the core of the Newtonian picture. Sir Isaac Newton described time as absolute, true, and mathematical, something that flows uniformly, independent of anything happening in the universe. Under that framework, reality is basically a stage. Space is the layout, time is the wall clock, and physics plays out as if the clock is not part of the story. This worldview dominated for centuries, until the early 20th century, when one set of ideas didn't just challenge Newton's model, it cracked it open. Albert Einstein didn't simply refine the Newtonian clockwork universe. His theories of relativity redefined what time even is. Einstein's special theory of relativity says time is not a single universal rhythm shared by everyone. It's relative. It depends on how you're moving. As an object approaches the speed of light, time for that object slows down compared to a stationary observer. This is time dilation, and it's a direct break from the classical idea of a universal ticking clock. The deeper shift is even bigger. Time and space are no longer separate containers. They merge into a four-dimensional structure, space-time, where changing your motion through space changes how you experience time. Then Einstein goes further. In general relativity, gravity is not a force pulling across distance the way Newton imagined. Instead, mass and energy curve space-time itself. Planets, stars, anything massive, warp the fabric of space-time, and that curvature dictates both how objects move and how time flows. This has a startling consequence. Gravity affects the rate of time. Where gravity is stronger, time runs differently than where gravity is weaker. A concrete example makes it real. Time runs slightly faster on a mountaintop than at sea level because Earth's gravitational field is weaker at higher altitude. It's a tiny effect, but it's measurable, confirmed using highly precise atomic clocks. And this isn't abstract theory. Modern life runs on it. GPS satellites orbit Earth at high speeds and sit in weaker gravity than clocks on the ground. Einstein's framework predicts two competing effects. Reduced gravity makes satellite clocks run faster. High orbital speed makes them run slower. When you combine them, the net result is that satellite time runs slightly faster than time at Earth's surface. If GPS didn't correct for that mismatch, navigational errors would build up at roughly 10 kilometers per day. So GPS systems continuously account for relativistic time dilation by adjusting satellite clocks to keep positioning accurate. By now, Newton's absolute time is gone. But here's the twist. Even with relativity, time is still treated as fundamental. Whether absolute or relative, it's still built into the universe's fabric. Then quantum mechanics steps in and makes the situation even stranger. Quantum mechanics often handles time in a way that clashes with relativity. Instead of treating time as a flexible dimension woven into space-time and influenced by gravity, quantum theory frequently treats time as an external parameter, a reference axis against which probabilities evolve. That mismatch is a major reason unifying quantum mechanics with general relativity has been so difficult. Relativity treats time as dynamic and gravity-dependent. Quantum mechanics often treats time like a fixed outside backdrop. One of the most mind-bending quantum phenomena is entanglement, when particles become so deeply linked that measuring one influences the state of the other, even across vast distances. Einstein hated the implication, famously calling it spooky action at a distance. But experiments have repeatedly confirmed entanglement's reality. And here's the uncomfortable part. The correlations appear without any time delay, almost as if distance and waiting time don't apply the way we expect. That puts pressure on the classical notion of causality, which assumes a clean temporal ordering, cause first, effect second. So if quantum reality can produce deep connections that don't seem to respect our everyday sense of temporal sequence, it opens a more radical possibility. What if time isn't the stage where quantum events happen? What if time is something that comes out of quantum structure? Some modern proposals suggest that time may emerge from quantum entanglement itself, not as a basic ingredient, but as a property that appears when parts of a system are related to each other in the right way. Page, Wootters, 1983. Time from correlations. A major idea here is the Page-Wootters mechanism, introduced in 1983. The concept is subtle, but the implication is massive. In an entangled system, time can emerge through the correlations between subsystems. In that framework, one part of a larger system can effectively behave like a clock, but the ticks are not coming from a universal time background. They're coming from the relational pattern you infer by comparing one subsystem to another. Without entanglement, the universe would appear static, unchanging, implying that time is not fundamental, but a manifestation of quantum correlations. This theme gets even sharper in quantum gravity. The Wheeler-DeWitt equation, used to describe the quantum state of the entire universe, famously omits time altogether. That absence isn't a trivial detail. It suggests a universe describable as a timeless wave function. In this view, time emerges only when you stop trying to describe everything at once and instead describe subsystems relative to each other, again reinforcing the idea that time may be an emergent property born from entanglement and interactions. If time is emergent, it challenges the clean split we've lived with for decades. General relativity treats time as a dynamic part of space-time influenced by gravity. Quantum mechanics often treats time as an external parameter. An emergent time perspective suggests a deeper theory could exist, one where space-time and time itself arise from more basic quantum processes that could help resolve long-standing conflicts between modern physics' two most successful yet incompatible frameworks. This is why emergent time discussions frequently appear alongside unification efforts. Emerging theories such as string theory and loop quantum gravity suggest space-time, and by extension time, may not be fundamental, but could arise from deeper quantum structure. In that framing, string theory is discussed as allowing time to emerge from deeper patterns tied to the vibrational behavior of fundamental strings within the space-time fabric. Loop quantum gravity suggests space-time is composed of discrete chunks, with time arising from how those chunks interact. If time arises from quantum correlations, then manipulating correlations could matter in fields like quantum computing and information theory, opening potential new ways of processing information. But the implications spill beyond technology into how we experience reality. Traditionally, we think of reality as a sequence, past to present to future. If time emerges from correlations, reality might be closer to a static block where all moments coexist, and what we call now could be something our minds assemble. This aligns with relativity's idea that all points in space-time are equally real, weakening the notion of a universal present. In that light, the universe may not be as dynamically flowing as it feels. Our lived sense of motion through time could be shaped by perception and interaction rather than by an objective cosmic clock. And that leads to one of the hardest consequences to stare at directly: free will. If all moments coexist, as suggested by a block universe model, then our choices could be predetermined, with the feeling of freedom functioning as an illusion, or at least not the kind of freedom we intuitively imagine. Finally, there's the role of consciousness. Some ideas propose that the brain imposes a sense of flow and causality onto a deeper, timeless quantum reality. Neuroscience shows the brain organizes sensory input into a coherent narrative of past, present, and future, sometimes described as mental time travel, a survival tool that helps us anticipate threats and plan ahead. If time is an illusion, that raises a blunt question. Is our perception of time a window into objective reality or a highly effective survival interface? Thanks for watching. If this exploration changed how you think about time, even a little, drop your thoughts in the comments and stay curious. We'll see you next time for more cinematic, science-first deep dives into the mysteries of the universe.